Maryland as postdoctoral fellow before returning to the work in India in 1983. His research interests include understanding the variability and prediction of Indian monsoon and how they are linked with the global predictable climate models. Professor Goswami has more than 185 publications in high impact peer reviewed journals and books. High level of citation of Professor Goswami publication is an indication of his impact on the current work on meteorological community. Uh, he has also won many awards like like from the Indian Meteorological Society and Fellow of the World Academy of Science, Tristly, Italy. He also received a Kalapati Ramanathan Medal from INSA and National Award in Science and Technology from MOES in 2014 and Lifetime Achievement Award in Science in Technology by Government of Assam. Sir, all the participants and the attendees have heard a lot of about you, and now we all are eagerly waiting to listen to your insights and knowledge on clouds, building blocks of weather and climate. Sir, we welcome you on this session. Thanks for accepting our request. I kindly invite you to deliver your session.
Thank, thank you so much. Thank you for the introduction. Let me try to share my screen and just let me know if it is working.
Yes, sir.
Is it
Yes,
visible?
sir. Yes, yes.
Yes,
Oh,
sir.
Yes.
okay. So, so thank you so much for inviting me, and I'm very glad to be around. Today, I'm going to talk about clouds. This basically the part of this lecture is basically very introductory to introduce clouds and how they are kind of building blocks for our weather and climate. And then towards the end of the lecture, I will talk about some of the important questions that we need to. I mean, there are a lot of unknowns about clouds and a lot of unknowns that still creates uncertainty in terms of our ability to simulate the weather and climate. And those issues, how we can address, we'll talk about that towards the end. So I'll start with basically some very simple questions. Like, we know that rain is essentially the source of life on Earth, and this is delivered by clouds. And we I think everybody wonders that some clouds produce a lot of rain, but many clouds are just hanging around, do not produce any rain. So we must wonder why some clouds produce rain and some clouds don't produce rain. Also, we must wonder why some places we rain more than the others. For example, northeast region of this country gets for example, seasonality, like we get a lot of rain in summer, but not in winter. Why? So otherwise, like there's a lot of rain in northeast region, but in the same latitude, Gujarat and Rajasthan gets very little rain. So we must also wonder why. So we must understand this. To understand this, we must actually understand these are all caused by clouds and the different types of clouds and environment that facilitates or prevents tiny drops of water to, in clouds to convert into raindrops. So this is the main, basically, the differences in the rain and not having rain depends on this conversion of cloud little droplets to raindrops. Most importantly, clouds are actually very fascinating subject. They have a lot of microphysical processes going on inside the cloud, and they have a lot of complexity and multi-scale organization. And this organization of clouds result in release of latent heat at different scales. And this latent heat happens to be the driving factor for weather and climate. For example, here we can see from starting from the raindrops, little raindrops which became like a cumulus cloud. So that became organized into tropical cyclones, which then get organized into ITCZ, can affect. So this indicates the kind of one of the most fascinating large-scale, multi-scale interaction in the atmosphere, and these affects our generally both weather and climate. And this will be basically some of my theme, where how clouds get organized, what is the basic processes that leads to the formation of the rain, and how they get organized into different structures, and then we'll raise some questions. So basically, first part of my talk will be basically some basic processes of clouds and precipitation process. Why importance of dynamics? Most of the time, cloud physics research has been done in our country, where it is isolated with dynamics is basically, but clouds cannot exist without dynamics, and the dynamics interaction between clouds and dynamics are very, very important, and this is something that I'm going to emphasize. Then we are going to I'll talk about multi-scale interaction and how that is key for our understanding that multi-scale interaction is key to parameterizations of the convection, and the parameterization is an essential part of weather and climate model. Although today, with more and more models are becoming very, very high resolution, maybe globally cloud resolving model, but that is only for special process studies. But on an operational sense, we still need parameterization in many models, and therefore the parameterization is a key issue, and that we'll see how we can understand multi-scale interaction, and then from there how we can how we can improve our parameterization. So my theme will be that we have to integrate cloud physics and dynamics, and that is what. So with that in mind, I will discuss one major program that I initiated at IITM called Physics and Dynamics of the Clouds, and how it had three different components: a sort of cloud aerosol interaction and precipitation enhancement experiment. There is a high altitude cloud physics laboratory, and there is also another laboratory experiments in clouds. So there is another component is here, which I have not shown here, but I'll show you some results of that. So then I'll talk about a little bit of a few preliminary results. I cannot go into the details, and I have also left this project long time, I mean almost 6 years ago now, but I still are in touch with some of these. So let us start with some observation of clouds. This is an observation. This is just a global picture of cloud in a particular day. You can see that these clouds. Tropics is characterized by this band of cloud. This is a very unique, it's a very interesting and important aspect of tropical clouds, which is the organized sort of long global scale organized band of cloud, and that is what we know as ITCZ, which is visible even on a day-to-day time scale. But that means it is present there almost all the time. They keep changing dynamically, but the structure keeps changing dynamically, but it is there all the time. And of course, there is a certain seasonal migration of this, but it is there. So that is why even if you average over a month, this is the same kind of a picture. Interesting structures all over the world, and they have their own implications. I will concentrate mostly on tropics, but so clouds get organized into this kind of a. This is another snapshot of ITCZ. What I want to emphasize here is just embedded in this band, there are vortices, and these vortices are mesoscale systems like this one, and there may be another one. These mesoscale systems actually, within the large scale system, there are these mesoscale systems which are embedded. And this is so the large scale. The ITCZ has a scale of about 10,000 kilometers, where within that we have these vortices, which are major scale. Sometimes they get into cyclones, and so there are a number of such major scale systems which get organized into a large scale ITCZ. And this system, of course, within this such a major scale system, or like a tropical cyclone, there are of course individual clouds. It is bands, and within the bands there are cumulonimbus clouds. So there are of course clusters of clouds. These bands are nothing but sort of clusters, but there can be sort of individual clusters also. So this is an example of clusters of clouds. That is another cumulonimbus cloud which is embedded into the cyclone. So this individual clouds, which have scale of about 10 to 20 kilometers maybe, are get organized into systems of tropical cyclone scale, which are of the order of 500 to 1,000 kilometers. And then all of that get organized into ITCZ, which is in the scale of about 10,000 kilometers. So this is a multi-scale interaction. That is, this is another example of eight cumulonimbus clouds. So this multi-scale interaction is a key dynamics of cloud. So there are some other fascinating aspects of cloud. This is a picture of wavy clouds, which was snapped on right over Brahmaputra here in Guwahati. So many times, again, there is an interaction between dynamics and the clouds. Here, these are not generally produced by gravity waves, which are produced within the environment. And if there is enough moisture near the level of lifting condensation, they start condensing. And where there is descending motion, they produce no cloud. So you get a sort of nice picture of a wavy cloud. And Assam is a region where there is a lot of gravity wave activity going on because of the mountains around it, and the winds interacting with the mountain produces gravity waves. These are a lot sort of inertial gravity waves. They are not very high frequency waves, but these gravity waves can produce such interesting pictures of clouds. This is another example of such things somewhere else. So this kind of a wavy picture of clouds are produced through an interaction between the dynamics and the moisture. So what are clouds? Clouds are nothing but manifestation of water in a liquid form. Can I reduce one? Okay. So essentially, a manifestation of water in the liquid, solid, or solid form in the atmosphere. They are composed of millions of little droplets of water or ice crystals. There are clouds, of course, also in other planets, like Venus has dense sulfur clouds. There is carbon dioxide in the atmosphere, and sulfur dioxide, they produce chemical reactions to produce these clouds. And so why does art have clouds in water? So art is a very interesting thing that about the Earth's climate is that the temperature distribution from equator to pole or from surface to the top of the atmosphere are all around very close to the triple point of water. And that is why our Earth, it is a unique planet where all three phases of the water can exist and convert from one to the other. There is a possibility. Now, conversion of from one state to the other state is associated with either release or absorption of large amount of energy, and that energy exchange gives rise to changes in the heating or cooling pattern in the atmosphere, and that heating or cooling is essentially can give rise to distribution of the heating distribution, and that heating distribution gives rise to motions and the circulation in the atmosphere. So especially in the tropics, where temperatures are relatively high, where the evaporation is very strong, and therefore these different phases can exist and produce a lot of contribution to the heating. And the heating is what drives the circulation, and the heating gradients is what drives the circulation. And that is how the clouds actually affect the tropical circulation and weather and climate. Uh, uh, how does clouds are formed? So essentially, as you know, the atmosphere is heated from below, so air is warmer near the surface, and as the temperature decreases in elevation to the troposphere, it decreases by about 6.5 degrees per kilometer. Uh, uh, but of course, also there is the pressure decreases with height. So these two things allows that if you imagine a isolated parcel of air to moving upward, then due to gas law, essentially it will expand and cool. And that cooling can lead to help condensation of water vapor and produce clouds, and that so air can become saturated. So first of all, to produce clouds, air has to become saturated and condense, and therefore, but it can be saturated in various different ways. One is you can add water vapor in a particular region. Suppose you bring in more moisture and put more water vapor, then of course it will try to saturate. That is one way of doing it. Another way of doing it is you can change the temperature of this particular environment. You can cool the environment by whatever means possible, and that will also increase the potential for becoming saturated and therefore condense. So generally how clouds form is essentially most of the time the clouds form basically if water vapor in the atmosphere is moves up and then cools and then condenses. So that is generally what happens. Now, so what are the necessary conditions? Basically, we have to have an uplift mechanism. So uplift mechanism will produce, suppose I'm not talking about the more moisture coming in from somewhere in a given region. You can produce condensation by uplifting. And that uplifting can happen through various different because of that process I mentioned. It will, when you uplift a air, it will cool. Then at certain point, the water vapor can saturate and condense. But it also requires a condensation nuclei. Now, why do we need a condensation nuclei? Because I'll come back to that in a minute. These two things are required. Uplift is required, but it also requires a condensation nuclei. Without a condensation nuclei, it will take very long time for water droplets to, or it may not even condense at all. And I'll come back to that in a minute, but let us see what kind of uplift mechanism is available. There can be heated air, which is convective uplift. So if there is very strongly heated surface, it will produce air which is much lighter and try to go up. And lighter relative to the environment, and then it will try to go up, and it is a potentially produce a cloud. There is also convergence uplift. So if there is somehow you can force the air to converge, this convergence will produce upward motion, and this upward motion can give rise to also condensation and then clouds. There is also orographic uplift. Suppose you move here against a mountain, the mountain will force it to go up, and that is same uplift will take place, and therefore possibility of condensation. This is something over the northeast in my own region. You can always see climatologically there is this band or this kind of cloudiness. The rains takes place and the cloudiness happens, and this is essentially because all around this valley, Brahmaputra Valley, there is this mountains. These mountains, because of these mountains, the air coming to the valley rises to against these mountains, produce rain, and that is how rain happens in the. It's a very simple mechanism. There is also something called frontal uplift. This has mostly happens in extratropics. Can happen here also sometimes. It's a very strong. So suppose you bring very cold air and warm air together. The cold air is more dense, and the warm air is light. So cold air and they will not have time to mix, and so the warm air will go above cold air. So it will produce an uplift, and that uplift can give rise to, and if there is a gradient already, suppose in a slope of a mountain this happens, it produces a strong uplift, and that can also produce condensation. So, but we need a condensation nuclei to produce these, and that is essentially is required because normally the cloud individual molecules of water are very small, and suppose it touch and the surface tension in this suppose another water molecule tries to get together and then become, they are so small that the surface tension force is too strong and tries to break it up. So they are normally very unstable. So you need to bring them to supersaturation of about 120 to start getting condensed. But even then it is very difficult. So unless we make the size little bigger, then this the hydrodynamic and gravitational force then can balance the surface tension force and make it stable. So that is why we need a certain, suppose around, instead of building on just a water molecule, suppose I have a slightly 1 micron scale or less than a 1/10 of a micron scale particle. On the top of that, if it starts building up, then you have a size which is stable, and then it can then add more and more and become bigger. So that is why we need a condensation nuclei. Condensation nuclei are some material, hygroscopic kind of material, which will attract the water molecule and make them remain over there. And there are many different. See, air pollution essentially provides us these air pollution. Some pollution can provide these condensation nuclei, and therefore they can affect the clouds. So the air pollution in some impurity, very pure air, there will not be cloud. Very difficult to produce clouds. So we need some impurity. Now impurity can come from various different sources. Sometimes natural sources like sea salt can also give you some impurity in the atmosphere, and those can form a nuclei. On the other hand, these pollutions of different kinds will always have certain chemicals in them, and some of them can be condensation nuclei. Now they can therefore influence the cloud distribution and affect the rainfall. Normally if you have a high concentration of CCN, they will start forming. Suppose there is a lot of CCN in the environment and you have a certain amount of cloud, then what will happen is that the clouds will try to form around all these CCN and then distributed the water vapor into a large number of small droplets, and they may not grow to bigger because there will be not enough moisture left, and therefore they will have to grow through collision and coalescence. And in the case when the drop size are relatively small, the collision coalescence efficiency is rather small, so they can stay, they hang around for a long time and not produce rain. So in a way, the pollution is required, but too much pollution can actually hinder the formation of rain, because it will distribute into a large number of sessions, and then it will not form into bigger drops to produce rain. So this pollution has this sort of dual effect, and can be so how does finally the rain take place? So the rain takes place essentially through what is known as rain or precipitation takes place. Precipitation can be in the form of rain or in the form of ice or snow. So the precipitation takes place through two different processes. One is called collision coalescence, and other is ice crystal method or ice crystal mechanism. So normally when basically also cloud have these two different suppose in a deep cloud you have normally you have two sections. One is what is called warm cloud below the freezing level. There will not be any ice or snow. On the above the freezing level there is a possibility of forming snow, so there can be something called warm cloud which is below the freezing level, and the clouds which are above the freezing level are called the cold clouds. So and their mechanism of formation are somewhat different, and the ice crystal formation also becomes important for the cold clouds. But the collision coalescence is there for both, but it is more important for the warm clouds. So normally the clouds are formed on these condensation nuclei. Then through turbulence and other dynamical effects, they'll start coalescing with other droplets and start becoming bigger. And then when it becomes bigger, slightly bigger initially, and then they'll start falling down. When they start falling again, they will collision with other particles, other droplets, and then start becoming bigger. And that is how these collision and coalescence. So collision will lead to coalescence of two drops, and this coalescence makes a bigger drop. The bigger drop will collide with another drops, and they become bigger and bigger. So this process until the gravity can allow is the friction. I mean, the friction is not sufficient to overcome. I mean, the gravity is able to overcome the friction, and therefore it falls down. So that is the process by which it falls. So it requires a certain critical size of the droplets to grow, and that it has to grow to that by through this collision and coalescence process. The ice crystal mechanism is actually very interesting because it happens. Somebody discovered that in a serendipitous way while observing the clouds. Bergeron is who first discovered this, and this is now called the Bergeron process. So what it does is essentially the main thing is that the saturation vapor pressure so saturation vapor pressure of just 1 minute. Saturation vapor pressure of ice is less than that of a droplet. So suppose there is coexist at this point. It is in this level, both water and ice are forming. So there on ice nuclei, the ice formed. There are certain supersaturated water droplets. These are coexisting. It turns out that the saturation vapor pressure of the on the ice crystals are less than that on the water droplets. So there is a pressure gradient, and as a result of that, the ice attracts the water vapor from the water droplets to be deposited on them, and that is how slowly it takes water vapor from the water droplets to come and deposit, and the ice grows ice crystals grow while the drops become smaller and die. So that is how the ice actually grows, because there is a very fundamental process which allows the water vapors to evaporate from the water droplets, go and deposit on the ice crystals, so this is how the ice gets deposited. So these two processes are very important in the formation of either ice or water in this precipitation. So let us look at quickly one. Let me show you how this is very dynamic. The clouds are very dynamic. They grow and die and grow and die. And let me show you a video where how a cloud grows and then finally produces rain. So this is a cloud. This is how a cumulonimbus cloud will do in a thunderstorm. So and you see that these are smaller droplets at the top, and these are bigger droplets. So the bigger and bigger droplets are happening, and then finally they will become so big, then they will fall into and produce rain. And these so this updraft and this, their updraft is produced through dynamics, and this updraft is taking the clouds to grow, and at the same time the pollution coalescence process is producing the bigger droplets at the bottom.
Goswami sir, 1 minute.
Yeah.
We are not able to see the video.
Oh, you are not able to see the video?
No.
Oh, okay. I'm sorry. How can I?
Sir, on the video, if there is any present mode,
1 second.
can anyone else help with it, if you know?
No,
video we could able to see.
It's okay. It's okay. I think this is. I'm sorry. I cannot see here anything. It is a movie which was saved.
Okay.
So saved in my computer, and then I can see it in my computer. So I'm sharing the screen. It doesn't go there.
Sir, slides. Yes, Rama.
Hello.
Yes, sir. We are
Once you stop the sir, if you can close the PPT, then we will able to see that.
Oh, I see. Then I have to
minimize the PPT, then we are able to see that.
Okay, let me see. Minimize the PPT.
Okay. Those connections are there. So,
can you see now? Can you see now? No.
It is not yet, sir.
No. Okay. Okay. I think it is not very very essential. It is just a visually interesting okay. Let us forget about it. Let us go back. Okay. Okay. Okay, so those are a couple of videos I had, but they're not very crucial for. So there are actually these we can different types of clouds. We can now screen is okay, right? Everybody can see the screen.
Yes, sir.
Okay, slide you can see. Okay, fine. So there are actually broadly we can divide various different types of clouds, and broadly we can define these clouds into a kind of a stratiform category and a cumulus category. Why we do this is because the particles, the latent heat that is released by clouds of these two different types are different, and they have a lot of important implications on the dynamics. It so happens that the cumulus clouds have a vertical distribution of heating which is somewhat maximum at the middle of the atmosphere and nearly zero at the bottom at the top. On the other hand, the stratiform clouds have large heating at upper atmosphere, maximum latent heat released in the upper atmosphere, and somewhat a little bit of cooling near the surface because there is some evaporation of these drops near the surface actually produces cooling. So this distribution is quite different. And these two, a combination of how much stratiform clouds are there in a place and how much cumulus clouds are there, cumulonimbus clouds are there, that makes the total heating function in any place, and that has an implication on what kind of circulation we are going to expect. So that is also important. Therefore, in any model should actually be observed, should be able to simulate the observed distribution of the stratiform clouds and the cumulonimbus clouds or cumulus clouds. So that is the reason I am just making this point here. So, but I think the most interesting thing is the multi-scale interaction of the clouds. So the individual clouds are fascinating by themselves, but their organization is far more fascinating. So as I said, that individual clouds produce cumulus clouds go into mesoscale systems, then tropical cyclones to ITCZ, etc. Now let me show you that and this is important, as I mentioned in the beginning, this is very much important in terms of understanding the multi-scale interaction is very much important to produce any kind of parameterization of these. So these cumulus clouds lead to the tropical cyclones. Tropical cyclones get organized into ITCZ, and this is actually involves a large is in a mind-boggling sort of scales. Starting from water drops, if you think they have of the order of micron size. If you then then they get organized into individual clouds of cumulus clouds of 8 kilometer or 10 kilometer size, then get organized into 1,000 kilometer size tropical cyclones, then get organized into a size of ITCZ, which is of the 10,000 kilometer. This involves a scale ranging 15 orders of magnitude, and that is a challenge. Now, how do you take, because ultimately to get these heating by the ITCZ correctly, to estimate the heating released by this correctly, I have to have the knowledge from or data from all the microscopic CCNs to distribution of clouds, to distribution of mesoscale systems, to this, and that is is a major challenge. How do you do that? To do that, you need a very, very high resolution model or cloud resolving model. Even in a cloud resolving model, 1 kilometer scale model, you will still not be able to resolve these. You will have to parameterize them. And therefore, still there will be certain errors and there will be certain uncertainties still there. So that is what makes the calculation of the clouds in weather and climate models a very, very challenging job. But organization, how does the organization take place? Organization are two different types. In fact, clouds organize into something called self-organization mode. These self-organization of clouds or self-aggregation of clouds is a very interesting subject, and there is a lot of studies now to understand how clouds themselves organize into like tropical cyclones, for example, or mesoscale systems. And then of course there is another kind of organization, like organization in like our MZOs or our monsoon ISOs. So in a very large scale, several thousand kilometer scale clouds get organized. These are also another kind of organization, and there is evidence of that. For example, in an active and break condition during monsoon, if I take organization of the cloud, I mean take composite of clouds when in many active conditions or break conditions, they show up structures like these which are very well organized. These are precipitation, but these are associated with exactly the same clouds. Are also organized exactly in the same sense, and so the clouds and precipitation gets organized in these scales during active and break spell. This is a monsoon ISOs. Similarly, this has a propagation of this organized cloud bands actually propagate northward, and so these are. So whole thing is very, very organized, and then the dynamics makes them propagate in an organized manner. So this is the question is, what makes them organize in this particular scales? And that similar thing happens in MGO, for example. The eastward propagation of the MGO is organized into this kind of structures, which then propagate eastward, and so there is a very similar organization. And that organization of rainfall and winds are associated with the dynamics. For example, here there is this is a velocity potential, this is winds. So the winds, velocity potential, and precipitation all are interacting to produce this organization. So within this organization of MGO, for example, there is another scale organization. This is a picture of high resolution picture of clouds, where this is the sort of cloudy phase of cloud which propagate eastward. But within this, it propagates eastward with a periodicity of about 40 to 50 days. But within them, there are clouds which propagate westward. These have a different time scales and spatial scales, which within the large scale organization of the MGO, which is in the global scale, within them there is also certain waves which are propagating westward and have a different scale. So this is what is multi-scale interaction I was talking about. So one scale is embedded in another scale, embedded on another scale, and they interact with each other. The other thing is the self-organization. People have now seen that by doing modeling experiments, this is a kind of review article on the convective self-organization recently published. So I took a couple of snapshots from there. This is a snapshot of a model with certain radiative convective equilibrium, temperature, and then you give some random perturbations, and these random perturbations then essentially grow, and after some time, like 80 days, they organize into certain structures, just a few structures. So, and this is nothing, no external forcing, nothing. This is just within this. So there is an interaction between clouds, moisture, radiation, surface fluxes, and circulation that leads to organization of these. This is a very, very interesting and very intriguing, and there is a lot of interesting studies now today to the self-organization. This has to do with the very self-criticality. These are a lot of work that is going on understanding the clouds as a part of this self-criticality in various other parts of science, physics, biology, and everywhere. This kind of self-organization is there, and the cloud is one of them. This is another article where our people from IITM are also involved in the self-aggregation in radiative convective equilibrium simulations. So you take models of different kinds of models, the models of different resolutions and physics, and then how do they get into this? So there is a sort of summary of this interesting study, and that shows that there's a variety of different kinds of models with different resolutions. And these are cloud resolving models. These are not cloud resolving, cloud permitting models, not really cloud resolving models. These are more or less cloud resolving models. And they show a somewhat different kind of. So there are a lot of things we still don't understand very well, but we are beginning to understand a lot about how they interact to produce the organization. The organization depends on the resolution of the model, the size of the art, and everything. So in a way, this has something to do with all the number of tropical cyclones. If you see over in a year, is roughly there is roughly a fixed number that happens. Now, this has something to do with this kind of an organization of clouds into self-organization of clouds into these systems. So Of course, today we can simulate these clouds, with various kinds of high resolution cloud resolving models. This is a kind of old picture from NICOM I took, and it shows this. Can you see this picture?
Yes.
Okay, so this just shows a simulation by a model of these clouds, which is quite realistic. This is, of course, I must say that this is a pretty old picture, almost 15 years old, and today there are a lot more details we can do and much better simulation our people are doing in different models, and you can find it in the literature, a lot of that. So what I'm saying is that we are beginning to with models, better and better higher resolution model with improved physics, we are able to simulate the distribution of the clouds in the atmosphere much more realistically today. And that is why many of the uncertainties are reducing. Although we cannot make these uncertainties in simulating this clouds go to zero, because there will be always some uncertainty, because even at very smaller levels, we have to have some assumptions into the closing the system, and that is why at some level we'll have certain amount of understanding. So how do I call these building blocks of, why do I call them building blocks of weather and climate? See, we see that the weather, like tropical cyclone, are essentially due to this kind of CISC process, where latent heat release is helped. The latent heat is released within the clouds through initial dynamical processes. This heat then produces the low pressure area in this. This will produce more convergence into the of moisture into the system, and they produce more clouds, and this intensifies the system. So the intensification of the weather systems are very much dependent on the latent heat released by clouds in the tropics, and therefore the weather system, the without clouds, the weather in the tropics will not be there. I mean, so weather intrinsically the clouds are kind of building block for weather systems in tropics, especially. In extratropics they are passive, they are not driving the systems, but in tropics the clouds are driving the systems. There also the ITCZ is essentially the driver of the Hadley circulation in the tropics. Hadley circulation is nothing but Hadley cell is our climate, right? So the Hadley cell is driven by ITCZ, because that is the heating that is released by ITCZ is where the ascending motion will be there, what will be the strength of the Hadley circulation is all determined by the ITCZ, and therefore the climate is also governed by ITCZ, the clouds in the tropics. So the clouds are essentially building blocks. So now let me come to the next few minutes. Let me talk about some of the research priorities that we need in the Indian context. So when I joined the IITM at that time, sort of 2006, there are a couple of things that I realized that that in the country there's very little work on really detailed work on cloud microphysics. There are a few like cloud physics, very isolated works on cloud physics in a laboratory scale, like at IITM some work was there. There are some physics department people have recorded the drop size distribution and tried to understand the sort of some statistics of the clouds, but very little work to talk about. So India was quite way behind in terms of the cloud physics and dynamics work. Particularly the interaction between dynamics and physics was very little. But even otherwise, there is need for India to get involved, because most of the coupled models have a very serious problem in simulating the Indian monsoon, and these biases were linked to parameterizations of convection in the models, and therefore. And the convections have their parameterization of convections have their limitations always, but the limitations seem to be more serious in the monsoon context, because the monsoon is a very unique region here with topography and the large ocean atmosphere contrast in a warm ocean surrounded by tall mountains and the land in between. So this gave a region where the interaction between the convection and dynamics is very strong, and unfortunately there was very little data or studies, process studies to link how small scale clouds interact with the large scale environment and improve the parameterization in this region. Other parameterizations have been developed elsewhere in the world where the systems are somewhat different. So there are certain unique properties of this region which needed to be understood in terms of this interaction between the large scale environment and the small scale clouds, and this was missing. So this is one requirement that we needed to do start in the study, do something in the country. The other thing that was important that was there is that there are a lot of demand of what is called cloud seeding. As I said, that there are certain times we have deficiency in rainfall, and during that time there is a demand that somehow we increase the rainfall by seeding the cloud. Now, how the seeding the cloud is essentially from that collision coalescence process. As I said, if there is not enough CCN, large CCN, the clouds will not produce rain. Now, so if I can physically go and put some more large CCN into the cloud environment, then maybe they will produce rain, and that is what has prompted a lot of cloud seeding experiments. But the problem was that whether the clouds would have, if you waited for a certain time, maybe cloud would have still rained a certain amount. But before estimating that, if we go and do seeding, then you will get some rain, but you will not know how much of the rain has come from seeding or how much it would have come from the natural processes. So without separating these two, it is difficult to estimate the efficacy of this. There is no experiment in this country to test that. Therefore, that was also very, very important. Otherwise, many times you can go and see it and nothing will happen really, not much change will take place. And that is because the environment is already having those kind of molecules and still it is not working. Those kind of CCNs are there in the environment and it is not. So we need to have a good idea about what is the distribution of CCNs all over the country, and then based on that, devise a technique, devise experiment to test the efficacy of such things. So that was also missing in the country, and that was required. And so these are two major objectives that was required. And based on that, with this thing in mind, I sort of initiate a major program in IITM, and that is called Physics and Dynamics of the Tropical Clouds. And it has three components. One is called CAIPEEX. It is the Cloud Aerosol Interaction and Precipitation Enhancement Experiment. There is a high altitude cloud physics laboratory. So this has to be in a campaign mode, with more focus on the cloud microphysics data, and these will be on a fixed platform, fixed point, but it will have continuous measurement and high resolution temporal measurement, so that it can complement each other to build up that knowledge about interaction between dynamics and dynamics and physics of the clouds. And of course, laboratory cloud lab is how the turbulence and other things can influence these dynamics. That can be studied in a controlled manner in a cloud. So we need all these three different. And fortunately, I was fortunate enough because at that time there were certain funding was because these required certain amount of equipments and certain infrastructure. That is, without that you could not do that. Earlier, people had that problem, that funding was not available, and people were not able to really mobilize that kind of funding. So fortunately, I was able to mobilize that funding for these and establish that. And these experiments have actually built up the facilities which are quite unique. So I'll not go into details of how these things have been done, but I'll just give a very brief idea that how aerosol interaction, cloud interaction, there is a lot of uncertainties. I could not go into detail here, but and those things we needed to understand. And so the from single environment to cluster, cloud clusters and the organized conversion, how it goes, we have to try to understand from these. So we had set up experiments in this region of the IITM is here somewhere. The Mahabaleshwar is here, where this high altitude cloud physics laboratory has been set up. And in the rain shadow region, we established a test bed where another there is one now there is a fixed C-band radar and many other equipments which is giving you and of course there are airplane experiments. All have allowed us to collect a whole lot of very precise, very important data, based on which now we can. So we can have a lot of very important science coming out of that. So the cloud seeding experiments, we had to do this because the cloud seeding was something that was required by government and country, that we have to that science we have to bring in. But so we built up this program in a way that piggybacking on this experiment, we can learn the basic science, basic physics, or basic microphysics, and for that, of course, we need different techniques. Like we need radars to monitor the clouds. We need measure the water cloud formation, etc. And then you have to seed using aircrafts or burners or rockets. We decided to use aircrafts. So there are three different types of seeding. One is glaciological seeding, where especially in the extratropics, the cold clouds. So you go and put either by rocket or through burners, you put aerosols, and so those scissions over in the cloud environment, and then it accelerates sort of it evolves into grows into bigger droplets and then eventually precipitates. So this accelerates the process of forming the droplets faster, and therefore produces precipitation. This is something called hygroscopic seeding, where in the warm cloud you do you again by either by rocket or through the burner or by airplane, you put in those scissions in these, and that eventually grow into bigger droplets and then rain. So even in warm cloud, in the tropical environment, you can do glaciological seeding, but it doesn't really is not. There is more moisture in this region, therefore you have more chances in this in the lower atmosphere. A lot more moisture is there, and therefore basically we don't do too much of glaciological seeding in the tropics, but we do more of
hello.
Yes. How much time do you have? Hello.
Yes, sir.
Sir, till half an hour is there, sir.
Oh, okay. I need only about another 10 minutes maybe. Okay, then we can have discussion. Okay. So So this experiment was conducted. IITM was the major national program. Of course, it was a national program, and we have involved many different institutes to participate. But IITM was leading this. Simultaneous observation of aerosols and cloud microphysics was done using aircrafts and local and instruments carried in aircraft. So the aircraft was fitted with various different instruments, and those instruments were very unique. It was kind of expensive, but I think it was worth it. In one of them, I had the chance to go. These are very small aircrafts. It's not very very comfortable, but and this is one aircraft that we. So there are several campaigns that were carried out. One that campaign was carried out all over the country. So to collect the background data on CCNs. So distribution of the countrywide sort of representative distribution of CCNs were corrected, and then we did campaign mode observation in this rain shadow regions. Several campaigns were there, a lot of collection were there, and then sort of double blind experiments on seeding were carried out, so that you could get a idea you have enough samples to separate out how much rain. Of course, simultaneously rain measurements through radars as well as ground-based stations were done, and so that if you have enough samples, then you could be able to separate out what is the natural effect and natural rainfall, and how much is actually coming from the seeding. But this now I am happy to say that now there is enough. This is carrying out those experiments are quite because you have to have the right kind of clouds, and whether there is enough cloud where possible to seed and all that. So in a given situation, sometimes in a particular season, you're stuck to a location which is around which you have to do, and it may be such that you may not get enough of the cases where you could do this study. So something like that, they had to struggle for several years. Now I think I understand now that there is a lot of sample, about more than 250 sort of sorties with different different environments have been done, and that gives us enough data to really resolve this problem. And I understand this has not been published, I suppose, and it has some paper has been, some white paper is being written by the MOES at this time. So this is supplemented by this high altitude station at which is now equipped. This was an IMD station, IMD building on which certain so we are of course always working in close collaboration with IMD, and IMD gave this facility to IITM to borrow some part of this facility to put all the equipment and develop a laboratory in that, where we modified a little bit and then produce this facility where all these equipments, the whole lot of equipments have been put in there. So cloud physics equipment, actually now you are not going into the atmosphere and you are sitting on the ground and then making measurements of the cloud parameters, because the clouds do come to the ground at this point, because Mahabaleshwar is a very unique position. It's a high altitude station where during summer the clouds are just going through this. Of course, we are only making measurements at the bottom of the cloud or the lower part of the cloud, not a vertical distribution, but at least we are getting a good distribution of clouds at that region. Then you have micro rain radar, there is astrometer, there is microwave radiometer, and so many different equipments, and of course all aerosol measurements. And so these gives a whole lot of high resolution data, which so these are the Scythian counter, video distributor, microwave radiometer, micro rain radar, cloud combination probes. All that is there, and that together with the basic meteorological, surface meteorological observation. Of course, during this time, they also have the facility to vertical profile of use radiosondes to do profiling of the atmosphere as well. During the summertime, that is also being done. So all these things together give us a huge amount of very, very unique data that has been coming out of this. So these are some of the instruments at Mahabaleshwar, cloud condensation probe, micro rain radar, etc., etc. This was it. Now this is supplemented by just nearby. There are 2 radars that has been installed. Now these are also very huge investments and facilities. One is cloud radar, and another is X-band radar. So these 2 radars together with these high resolution measurement, the radar also can give you high resolution measurement of the rain distributions and the cloud distributions as a result of this, and the meteorological parameter high resolution measurements are coming from the microwave radiometer and other things. So you have all that is required almost in this environment to understand the dynamics and the physics and dynamics of these clouds, and that is the unique property of this. So there are several studies have come out. I don't want to go into details, and neither do I have the time. So many important studies have come, what broadly what I'll say is that I think it has given us today. I think today I think India is in the map of the cloud physics and dynamics in the world. In the world, the studies, there are a lot of studies in many other places, but India was nowhere in the picture. Now today, India is in the picture. Look, in the scientists from IITM and now into this review programs of some of the major programs that also what we had done is this cloud physics fluid dynamics laboratory. So this is headed by a young scientist by Sipsai Dixit. He has developed actually also equipped with very fascinating and high-end diagnostic techniques and so we can study the turbulent processes or also some of the physics that is involved here. It is beginning to come. So far they have studied some of the boundary layer effects and how that could influence the physics. So some interesting papers are coming out in physics of fluids and things like that. So some very interesting results are coming out of these, and I don't want to go into details. You can go to IITM website and you will see some of those. So in conclusion, what I want to say is that this concept of physics and dynamics of cloud, we need an integration of in the country. It was needed that integration of dynamics and physics be made, and from there we should collect enough data to understand the dynamic, the interaction between the small scale clouds and the large scale clouds. And this particular program with all the CAIPEEX, the HSAPL, and the lab is providing a unique facility at IITM, which is probably unique in the world. And I'm very happy to see that now it is bringing out a lot of good work from that study. I am, of course, I think that a lot more could be done, but I think the beginning has been made. And I'm very happy to see that some of the scientists, I'm proud to see that some of the scientists are coming up in these review papers, like where the global community is taking in IITM also into this community to produce. For Tara is a member of this another review on precipitation enhancement research in the world, which is published in BAMS. This is published in GEMS, and so this is showing that I think with enough support and this, we can do great research in the country. And all we need to do is to identify the right kind of problems that we can tackle. But certain amount of support from the funding agencies are very important. Without that, you cannot have this kind of research. So I was very fortunate that that is the time we could. I think today probably it is almost becoming impossible to do this. So I am really happy that this was done at that time. Okay, with that I'll stop, and I'll be happy to answer some questions if there is.
Uh, to the participants, if you have some question, kindly put in the chat box. Sir, there's a question by Gayatri Fonia ma'am. So she's
Okay.
asking, what is Taumi effect and triple point of water in reference of clouds?
Oh, triple point of water is already explained here. Okay, so triple point is a well, just 1 minute. Tommy effect is that I'll explain Tommy effect. Just 1 minute. Give me this. So triple point is nothing but, see, basically this is 0 degrees, right? So 0 degrees is essentially is kind of around 0 degrees. You can have either depending on the pressure and temperature, you can have the water to be either in the liquid phase, or in the vapor phase, or even in the solid phase at the same temperature. Almost very close to the same temperature. So that is why it is called a triple point. So it so happens that so it is the pressure differences and the temperature differences in the earth. From equator to pole, there is a temperature gradient, right? Equator goes to temperature cools to pole, and from surface to top of the atmosphere also temperature cools, and the pressure changes. So these change in pressure and temperature are very close to these, happens to be around 0 degrees, where the triple point of happens of water. So as a result, and that is what makes it very easy for water to transform, either stay in water vapor. So suddenly the same amount of water vapor here, if I take it to a colder area, I can condense it. So that is the kind of change the state. Or or I can bring that the rain and take it to a slightly warmer different area, and then it will evaporate and becomes rain will become vapor. So this happen, our climate is such that the Earth's climate is such that all these three can happen within this environment, and that this is because precisely because we are just critically around this triple point. Our temperature distributions and pressure distributions are just around this point, and as a result, the changes in the different states are possible, and that makes a huge difference because in terms of the heat balance, and that is why the role that water vapor can play in the dynamics of the atmosphere and the circulation and thermodynamics of the atmosphere is so critical. Okay, the Tommy effect is essentially, Tommy effect is nothing but that process that I mentioned, that just let me, so this was the delay of the rain process due to the enhanced aerosols, which is essentially related, known as Tommy effect. Exactly maybe slightly different, but basically fundamentally this is what it is that the aerosols are needed for decision, but too much aerosols or the high density of aerosol, high concentration of aerosols can give rise to okay, now let us come back to this. Basically, what happens is that the drop size distribution, the precipitation depends on the drop size distribution of the, how much rain will take place will depend on what kind of drop size distribution is there in the environment. Drop size of water drop size distribution in the clouds. The clouds can have different water drop sizes. The small drops, they coexist with large drops. Now, if the large drops are more, then the large drops will fall down, coalescence will quickly produce rain. But if large drops are less, the drop size distribution is such that there are more small drops and very few large drops, then the coalescence process cannot become effective, and it will take much longer time to become big drops and then rain. So that delay in the rain process is due to change in the density, change in the frequency distribution or the distribution of the water drops within the clouds, and that change in the distribution. So when you add too much of aerosols or the polluted aerosols in the atmosphere, then what you do is you change the distribution such that you have now more small drops and less small big drops, and therefore the rain process gets delayed, and this process is known as Tommy effect. So we have to, most of the time in a polluted environment, that is what delays the rainfall. However, there is an opposing effect also, but not doesn't happen all the way. Sometimes aerosols can invigorate the cloud if it is somehow somehow associated with some very strong convective events. Suppose there is a lot of heating in the surface and there is a small scale distribution, and but the convective heating, if it pushes the pushes the airdrops all the way to the freezing above the freezing level, then they can quickly become ice, convert into ice. Now, when they convert into ice, they will release more heat. Then the upper atmosphere will get heated up. Now, when the upper atmosphere gets heated up, then they will produce stronger convergence. This convergence will then further enhance these formation of clouds and precipitation. So, in some cases, they can still produce invigoration, but in general, they will have a tendency to produce delay the rain process. Is that okay?
Thank you very much, sir. So, relating to the same, there's another question by Praveen, sir. So, he is asking what is typically used as a CCN for experiments?
Okay, so the cloud seeding experiments, there are several hygroscopic materials that are used. I will not go into great details because this is also a research material. Initially, simple salt was used, just normal salt, because salt is a hygroscopic. So you can carry in 70s. IITM actually made a cloud seeding experiment, and they carried, there was no sophisticated mechanism, in an aircraft, it was filled with salt, and the salt was being distributed, okay? And this is a huge cumbersome work. It is not very effective. Now, what people do today is either put something called silver iodide. It is also a hygroscopic material. So you have, these are you can create them in the laboratory of particular size, like 5-micron size or larger size. So this kind of material you can take in the aircraft and also just throw it in the cloud. But there are also, this has become more sophisticated today. So these aircrafts are now connected with certain flares. Let me see where was that picture. Let me show you one picture. See this aircraft has a flare at the end of this thing. There's something called a flare. So there are certain chemicals. If you burn them, they will produce a certain hygroscopic particles of a given size. This has been done with a lot of laboratory experiments. So these flares are now connected with the aircraft. So as they go on, they simply fire these flares. These flares burn, and as they pass along, leave behind a set of aerosols which are loaded with certain hygroscopic chemicals. I exactly don't remember what is the chemical that is coming out, but it is something like salt and silver iodide, something of that form that comes out of this and then gets distributed in this region. So there are a variety of these, and there's a lot of research is going on in the laboratory, which are what size and what chemicals are most suited, and that's also now then people go and actually make experiment in the field using them. So fundamentally, any hygroscopic material is good, but for practical purpose efficiency, you have to test it in the laboratory, which is more efficient, and that is how they decide on one of. Excuse me. Okay. Anything else?
Yes, sir, I think now we'll take the last question.
Okay.
One, sir. So it is by Daniel Simon, sir. He's asking, while doing the cloud seeding, do we have to consider the moisture concentration at the location before seeding?
Oh, of course, very much. Very much. That's a good question. You see, the cloud seeding is a very, very tricky business, because if there is not enough moisture, even if you seed, it will not rain, because you need a critical amount of moisture. So you must have some clouds in the environment, and in fact, we keep looking at clouds normally. What they do is that there will be a lot of clouds and they are not raining. We know that, and if there is enough cloud but not raining, then we know that there is certain amount of moisture. So you look at through radar, you keep looking at radar reflectivity. And radar reflectivity gives us what kind of distribution of water droplets are there in the clouds. So this reflectivity, it is something of the order of 40 dBz or less, more than 30 dBz, and that gives us certain critical. I forget exactly 30 or 40. So one of these around gives it. If it is below that, even if I go and see it, it will not rain. Only if it is around exceeds that, but still not raining, then only if I go and see it, it will rain. So that gives you a sort of kind of critical amount of moisture that is required. But for some dynamic reason, it is not raining. So what you are doing, you're just tweaking it a little bit, go there and put some CCN, bigger CCN, so that the collision becomes more faster, and therefore it rains. So it somehow overcome that dynamical inhibition which is not raining. So you have to have that critical amount of moisture. Already you need the moisture. Without moisture, it is a very dry environment. It will not work at all. So you cannot do this. So the seeding is actually a bit of a misnomer. Okay, it's not a very. I am never a fan of seeding, but we want to understand the science. And we want to understand also quantify this, what is the problem, and that is why this experiment was carried out.
Thank you, sir. Sir, we have next question from Millie Madam. So she's asking, sir, what cloud parameters we should take into consideration for the study of lightning events?
Okay, lightning events is again, lightning is essentially due to ice, right? So you need ice formation in the clouds, and also mixed phases of clouds. So when the ice and supercooled water collide, and they produce this charge separation. So the charge separation is that builds up and then produces the writing. So for that, you essentially need enough enough big size big size droplets. So this, when they fall down, basically they collide and then produce the surge separation mode. So if there is a hanging around, there is probability of surge separation becomes very weak. So therefore you need big drop size distribution. So you have to monitor the drop size distribution. So you can do that by radar, or you can do that by in situ measurements like a aircraft. So you can go inside the cloud and see. So lightning measurements are done by separate things, but to the lightning happens only when there is the drop size distribution has a lot of big droplets. So drop size distribution has to be towards the big size. So that is the critical parameter that I would say is important. But what was the question? Actually, I did not get. Is the question regarding
Like what parameters should be taken care to study the lightning effect? What cloud parameters should be taken care? That was the question by Millie.
Well, cloud parameter to lightning effect, you have to measure lightning, right? Lightning is now measured by some satellite or lightning detectors at the surface. So you first measure the lightning, how much lightning strike, or you measure, also you need to measure the electric field inside the cloud. So that is something you have to measure in a different way. That is difficult to measure. You need but at the surface you can measure the electric field. So you have to link the electric field inside the cloud to the surface electric field. So this kind of thing, several of these things are also being done at IITM, these studies. Together with that, you have to have microphysics information like the drop size distribution. So these are the things that you will need. You will need drop size distribution and the measurement of ice and the mixed phases like water and ice. It as a vertical distribution of that. So these things, some of these things now can be obtained from satellite like CloudSat data, and some of these in a larger scale you can do that. But on an in situ, in a detailed manner, if you have to do, you have to use these probes that I mentioned. The cloud physics probe can go and make measurement of all the distribution of the drop size distribution, the CCN, and how much CCN is there, what is the drop size distribution, and the cloud liquid water, etc., etc. All those things need to be measured together with electrical field information.
Thank you very much, sir, for answering all the questions by the participants. They have a more question for which I think we can connect later.
Okay, thank you.
Thank you, sir. You started with the basics with very beautiful and fascinating pictures in your slides explaining the concept. Then you proceeded to share the direct and indirect impact of aerosol, types of clouds, and the challenges in modeling. You also told about the cloud seeding experiment and its associated problems. You also gave a tour of Ganga Basin experiment conducted in this field and the Mahabaleshwar radar. So we sitting at our place could see the pictures of it. Sir, today India holds a place in the cloud physics across the globe, and we all applaud your contribution to make this happen.
Thank you, thank you. Thank you.
Sir, we extend our heartiest gratitude to you for acceptance to take this session. Thank you, sir. To the participants, now it is a break time for a few minutes only. And the web program will resume back at 11:35 a.m. I request all the participants to kindly enjoy this 5-minute break and be back by 11:35 a.m.
Thank you very much. I will now leave. Thank you.
Yeah. Thank you, sir.
Thank you, sir.
Thank you, Chandrasekhar.
Yeah,
Bye.
thanks a lot, sir. Yeah.
Bye.
Bye.